So it turns out there's actually two ways to do hypothesis testing. I personally am a fan of the p-value method. It's done in most journals. P-values are basically distribution agnostic, so it doesn't matter whether you have a Z or a T, the p-value means the same thing. But some books and some professors will teach what's called the critical value method instead, using these rejection regions. So exercise 7.4.3 is to sort of show you that we don't have to get p-values to make our decisions, and what you might see in another stats class or done by someone else using statistics rather than what we do in this class. So here you can see we're dealing with a random sample of n observations, and we're going to go ahead and specify the rejection region. So for all of these, let's go ahead and we'll do them for both, a Z and a T. So let's assume first that this is for a Z. So we're doing a right-tailed test. If we were to draw our little picture, the null would have been that mu was 15, and we want to know what values here would give us a rejection, right? Anything where the p-value is less than 0.10, less than our significance level, would be a rejection. Now that's in our standard. We could even go all the way back to the sample means, but they want us to actually do this for a z-score. Because once we see a z-score, we know a z-score gives us a measure of how unusual something is. So if we just came up with a cutoff for the z-score, we don't have to go all the way to the p-value. We could just look at our z-score and compare. So if this is our case that we're in, and we want to figure this out for a z-score, well, that's simple enough. We would just come over here and we would do our inverse norm, which we know so well. If the right side is 10%, that means the left side is 90%. So 1.28. So 1.28 would be the cutoff. So we would reject if we've got a Z greater than 1.28, and we would fail to reject if Z was less than or equal to 1.28, right? So anything in this region would be rejections. Anything in the opposite region would be failing to reject. And we could do the same thing for the t-test. And this is where it makes a heck of a lot more sense to be doing this, especially if you're doing this without technology using that table. So if we're doing a t-test, t is the same thing as normal, still got our bell shape, still symmetric, still unimodal, still centered at 0, just like our standard normal. So same idea. We want no more than 10% in this curve if we're going to reject, right, in this right tail. So we need to figure out what this t is. Well, if we're going to go to our table, we need our degree of freedom, right? So, okay, cool. That is, in this case, they gave us an n. This is 25 minus 1, or 24. So, okay, let's look this up. Oops, that's not what I wanted. In the table. So as I said, this is where the table gets a lot more useful, because the table is already set up so that it has upper tail probabilities, right? And we just said we want our upper tail probability to be at most 10%, that we would like the probability here to be 10%, and we'd like to know what the heck our t was, right? So we've got our 10%. We found out that our degree of freedom was 24. And now this is a heck of a lot easier than that weird range thing that we're supposed to do to find a p-value. 1.318 is what we are looking for. So 1.318. Anything greater than that would be rejection, because it would have a smaller amount of area in the curve. And anything, did I say smaller? I don't know what I said. But anything bigger than that, whereas anything smaller than that would be fail to reject the null. So our rejection region would be any t greater than 1.318. All right? So if you want to try out the next one, I'll go ahead and break it into another video. But like I said, I'm not going to test much on rejection regions. It's just a different way of looking at it.